Okay, let's get started again. The tangent line to a graph to the graph of a function. My grammar is bad here. To the graph of a function of f of x. Excuse me, not of. The tangent line to the graph of a function f of x at a point c f of c is the line that best approximates the behavior of the function f of x at points that are close to the point cf of c. It's the line of best approximation, so to speak. This definition is informal. The real one involves epsilons and deltas, and I don't want to go there. I don't want to delve into analysis or advanced calc. Okay, so really tangent line is hollow. The tangent line at a Cartesian point c comma f of c of the graph of f, that's the line of best approximation for points that are extremely close to cf of c. The line that best approximates the y values of points that are very, very, very close to the point cf of c. The line is exact at cf of c itself. Now, for points that don't equal cf of c but are very, very, very close to cf of c, it is the optimal line of approximation. You can have other lines that approximate quite well, but it's the best, the tangent line. It approximates the y-coordinate. Like if I have a very small delta c, and I consider c and f plus delta c, or c plus delta c and f of quantity c plus delta c, where delta c is very small but not zero. Well, that point's going to be very close to this main point right here, and the tangent line, the y-coordinate of the tangent line and the x-coordinate of the tangent line, well, they won't exactly equal c plus delta c and f of c plus delta c. The x and y coordinate of the tangent line. Let me back up. If we're at the tangent line, let's say that I go to the point on the tangent line where the x coordinate is exactly c plus delta c. Then the y value on the tangent line, it won't quite equal f of that c plus delta c, but it will be so close it's not funny, okay? That's our tangent line. I did a video on that a while back. This is kind of redundant because I did a video on this several videos ago. Okay, let A be less than C less than B, and let D be a real superset of AB closed. Let F be a function from D to R that is differentiable at x equals C. Then the equation of the tangent line for f of x at x equals c is given by this equation right here, and this form right here is called point slope form, based on the point c f of c. Notice that the derivative is the slope of our tangent line. You know, we've really talked about this already. I've already sort of gave this away a little bit in previous videos, or at least one previous video. This gives us a visual interpretation of the derivative, okay? I just wanted to go over that, and let's do an example. Let f be the good old parabola, okay? Consider the point negative 3, positive 9 on the parabola. After all, if x is negative 3, which I'm picking on, negative 3 squared is positive 9. The slope of the tangent line to y equals x squared at negative 3, 9 is, well, f prime of negative 3 equals the limit of the difference quotient to get the derivative. Limit x goes to negative 3 of x squared minus entity negative 3 parentheses squared. Those parentheses are important. Over x minus negative 3. But x minus negative 3 is plus 3. Now watch out. On the top, however, negative 3 does square to 9, but this negative here in the middle, guys, it's not going away, okay? So we get that. So we get x squared minus 9. Now, if I factor x squared minus 9, I get x minus 3 parentheses times parentheses x plus 3. But then that I kind of skipped that step. But anyway, that x plus 3, the golden goose is that x plus 3 is going to cross cancel with this x plus 3. You can insert that step in between if you wish. And you'll get limit x goes to negative 3 of x minus 3. Again, difference of squares, x squared minus 9 is x minus 3, x plus 3. And I probably should put that in. If you were ever in a calculus class, your professor might not approve, she or he. So x goes to negative 3 of, and then, so I'd have x minus 3, x plus 3. Sorry for the pause, let me just get this typed. It's bothering me not having that there. That's the difference of squares factor step. And then the golden goose. I need that step here because that lets me show the golden goose step where I cancel the x plus 3's and I just get the x minus 3. And I put the parenthesis, you need the parenthesis here kind of because you need to indicate that it's all inside the limit. Well, to be frank with you though, even, you know what, it doesn't matter. The limit's going to break apart anyway, and 3, that negative 3 is just a constant. So I can just throw negative 3 into x here. I get negative 3 minus 3, which is negative 6. That's my slope of my tangent line. Now that's good. That's my slope. But the equation of that's going to be, now I've got my m. Remember, derivative is slope. If you were to break off the graph and go flying off on the tangent, you know, you'd get the slope. So I do y minus the y coordinate of the coordinate I'm picking on, which remember is this guy. So y minus 9 equals the slope, which is the derivative, neg 6, parenthesis, x plus 3. Okay, now this is called point slope form. Now, if you want to go to slope intercept, you'll distribute the negative 6, rearrange, and you'll wind up getting y equals negative 6x minus 9, and that's the so-called slope intercept form of algebra. So these are both these are equivalent, and they're just the equations in different forms for your tangent line. They're the equations of it. To go from the former to the latter, again, just rearrange, distribute, and all that good stuff. Okay, we'll distribute and then rearrange all that. And there's that note we were talking about earlier. A vertical line has an undefined slope. We can't really assign either infinity because there's no way of knowing which one to assign. Okay. Now, that was going back to the previous video, that previous comment. Now let's move on. Okay, let f be a function from the reals to the reals such that f of x equals x squared for all real x. Consider the point negative 1/5, positive 1/25 on the parabola. Again, if I square this x coordinate here, I get this y coordinate here. So the slope of the tangent line to y equals x squared at this point. Now the tangent line is hollow. I need to say the tangent line at what point? This point right here. So is f prime of negative 1/5, which equals this limit of this difference quotient. And again, up here I get x squared minus 1/25 because this negative squares away, but this one here does not. And then downstairs, I do x minus a negative, which is x plus 1/5. And then again, I kind of committed the same offense on this example. Let me insert this step. You do difference of squares again. X squared minus 1 over 25 is going to be x minus a fifth times x plus a fifth. And let me do that now. So I'll try not to pause in silence. And you know what? I did a copy and paste, and I forgot to turn that negative 3 into negative 1/5. That's even worse. So sorry guys, I'm getting clumsy and just downright sloppy here. So abide with me. I try to avoid this stuff, but it happens to me anyway. So now everything's going haywire. So let me get this here, and let me get this here. So let me factor, and I'd get x minus 1/5, and then, well, x plus 1/5. Sorry for the pause, guys, and the delay. And then over x plus 1/5. Oops. And then that's no. Sorry, everything's going haywire. So let me get this typed in. And now the golden goose is I can cancel these x plus 1/5. They're what caused the 0 over 0 that I want to get rid of so badly. And then I need to get rid of this negative 3 down here, don't I? So let me do that. So the x minus 1/5, that's good. And let me get rid of this neg 3 and change it to negative 1/5. Whew. Okay, so my copy and paste, my perception is a little rusty and I forget the little things. So these cancel, leaving you with just this x minus 1/5 up here, but the denominator is just now 1, so it's understood. We don't have to write it. And then by continuity, just throw negative 1/5 into x. We get neg 1/5 minus negative 1/5 minus ordinary 1/5. But that's negative 2/5. Okay, so neg 1/5 minus 1/5 is negative 2/5. Okay, so there's that. And so, this guy right here, the limit x goes to, now sine squared to 1 over x is a wild guy by himself as x goes to 0, but x squared is going to dampen him greatly. So the limit as x goes to 0 of x squared sine 1 over x. Now, we got a hunch. We're going to define our function f such that f of 0 equals 0, okay? So we got a hunch that 0 would be our continuity point of choice. So if f of x equals x squared sine 1 over x for non-zero points, and if we define f of 0 to be 0 just because of a hunch, it turns out to be a good hunch because that makes us continuous. It makes us differentiable. Okay, so we get the limit as x goes to 0 of x squared sine 1 over x minus 0 over x minus 0, which is the limit as x goes to 0 of x squared sine 1 over x. That minus 0 didn't amount to anything. But this x squared over x, that just leaves an x up top, and the bottom is gone. And you know what, guys? I need a parenthesis here because, this time it's all inside my derivative, and it would be a disaster to take stuff out. That would not be good. So let's do that. Okay, but by the squeeze theorem that we've talked about, this limit is 0. Okay, thus if f is a function from r to r such that f of 0 equals 0 and f of x equals x squared sine 1 over x otherwise, then f prime of 0 exists and equals 0, and f is differentiable at the origin. You know what? A similar argument shows that an analogous result holds for f of x equals x to the n sine 1 over x if n is greater than or equal to 2. Now, we run out of luck if n equals 1, though. In fact, we might, if n is, now it's a little sticky if n is between 1 and 2. I'm not going to go there. You know what? If n is greater than 1, we should be good. I can strengthen this. N greater than 1. Because even if I had x to the 1.001 power, I subtracted these, I would still have x to the 0.001 power, and that ultimately will squash this to 0, because it goes to 0. This just swings between neg 1 and 1, but that's not going to skewer this guy. If it goes to 0 even slowly, this term is still not going to skewer this term, even if this guy right here goes slow to 0. Okay, so I can strengthen this to n greater than 1. Now, we run out of luck if n equals 1, though. Now, if we hit 1, we're in trouble. If we go below 1, we're in trouble as well, even more so. But let's just let n equal 1. Then I get x to the 1 right here, okay. But then limit x goes to 0 of x to the 1 times sine 1 over x, this guy right here. Well, the minus 0 doesn't mean anything. Well, that's okay. But these x's cross out, that's good. But there's a problem. We're left with sine 1 over x. And that swings wildly, which that limit does not exist. Oh, so the function, and I'm sorry I had to go down to the next page, f of x equals x sine 1 over x, if x does not equal 0, and f of x equals 0, is not differentiable at x equals 0, unfortunately. Even though it is still continuous there, since this limit right here equals 0 by the squeeze theorem. So the squeeze theorem saves continuity, but differentiability is not savable here. Oh, just because you're continuous at a point doesn't mean that your slope is settling down. That doesn't mean that you're particularly smooth there. So there's that. And I'm sorry, this needs to be spaced, and I'm moving on to a new idea. My spacing got messed up there. Okay, here we go. Now next, a separate example. Remember the wild function f on the real such that f of x is x squared if x is rational and f of x equals 0 otherwise. Now note that the limit as x goes to 0, if we would have defined f of x equal x squared everywhere, this limit right here is 0. And if we had defined f of x to be 0 everywhere, on the other hand, the limit would have still been 0. And so f prime of 0 equals 0. Guys, you know what's wild? F is differentiable at 0 and hence continuous there, but it's not even so much as continuous at any non-zero point. It's discontinuous at all the other real points. Like if you pick a domain x value that's not 0, f is going to be discontinuous at that x value. That to me is wild and crazy. It's true. Wildly enough, it's not even continuous anywhere else. I find that fascinating. You might not, but oh well. So there's that. And quiz. Big hint, it's going to turn out like if f is x cubed at the rationals and 0 otherwise. Is f differentiable at x equals 0? Big hint. Yes, it is. Justify it like I did up here, though. Okay. Is it continuous at any non-zero point? And no, it's not. You don't have to worry about justifying the second part, but there's that. You have an infinite hippity hop. You would jump up and down forever and ever. You would zigzag forever. But the thing about 0 is, yeah, you technically keep zigzagging, but you keep gluing in though. You get your jumps become less and less high, and at 0 your jumps become 0 in elevation. Like if you're over here at +1, you would go zoom, 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 zoom. You keep jumping back down to 0 and up to x cubed of whatever x is. But you infinitely wildly jump. But as you zone in on 0, notice my cursor, it's less and less wild, and then it dampens off completely at 0. And then it instantaneously, once you get to the left of 0, it's going to start zooming again. Even if you're close to 0 but not equal to 0, you're still not continuous there because there is still a little bit of hippity hop. Okay. Now there is a function that's everywhere continuous but nowhere differentiable, and I don't want to construct it. It's a little bit on the weird side, and but I'm just going to let you know that there is such a function that exists. Okay. Now let me move on to this one. Consider the limit h goes to 0 of this guy right here. This is 3 plus h to the 5th minus 3 to the 5th over h. You know what? That looks like x to the 5th. This looks like the derivative of f of x equals x to the 5th evaluated at x equals 3. Big, huge hint. That's what it's going to be, too. The second version of my derivative, of our derivative definition. So we push the limit as h goes to 0 of this guy minus this guy. Now, you're going to have to do it by brute force or use Pascal. You'll expand it out like this. You'll have the 1, 5, 10, 10, 5, 1 pattern. And then this dangling minus 3 to the 5th here that was already there. But this 3 to the 5th and this 3 to the 5th will cancel each other, and you'll just be left with your Pascal terms. If you don't do it by brute force, that's okay. You'll get the same thing. It'll take you a long time, though. And that'll equal the limit as h goes to 0 of, but hey, guys, the golden goose. We can cancel this divided by h down here. We can cancel an h from each of these terms down here after we divide off that h down here. So I'll go ahead and divide off that h, and that's just going to leave me 5 times 3 to the 4th is going to be alone, and this h squared becomes h to the 1. This h cubed becomes h to the 2, or h squared. And this h to the 4th becomes h cubed. This h to the 5th becomes h to the 4th. All right here. But then, that was the golden goose, because now we don't have 0 over 0 format. We can throw h equals 0 in and get this guy right here. But all that survives is just this guy right here, the 5 times 3 to the 4th. These other guys are gone because they still have at least one h in them. And then, so we do PEMDAS. 3 to the 4th is 81, and 5 times 81 is 405. Hence, we have shown that for f of x equals x to the 5th, f prime of 3 equals 405. And so there's that. That's a good test question, by the way, in a real calculus class. And I will leave it to you to do this example right here, guys. That's for you to do on your own. Thank you. That'll be all for this video. I'll see you on the next video.